Welcome back to another episode of Adventures in Machine Learning. I'm one of your hosts, Michael Burke, and I do data engineering and machine learning at Databricks. And I'm joined by my co-host,
Ben Wilson. I write code at Databricks.
We'll take it. Today we're going to cover Ben's background and how he essentially transitioned from data science to software engineering. And I have a couple of interesting questions teed up about basically how he thinks and how nature and nurture has impacted the way he approaches problems. And hopefully I'll be able to contribute a couple of my experiences as well. So without further ado, let's dive in.
Sounds great.
So how about you kick us off with the very beginning of your career? What were you doing? What was it like?
The very, very beginning. Well, out of high school, I joined the U.S. Navy. No, the beginning of my tech career would be my transition from what I used to do many, many years ago when I got out of the military, was work in traditional engineering. And that was applying my knowledge that I gained in the military of mechanical and electrical engineering into something called process engineering, which is you work at a factory, there's some tool or some technology that you need to improve or adapt or make better in some way, like enhance it, or just doing recipe control, where think of it like you're a baker and there's so many ingredients. You need to figure out what quantities of those ingredients and how to mix them together and how to apply them. And that's how things are made in factories. So process engineers control those machines and how they are used to make things. And I did that in a number of different types of industries and found that while incredibly fascinating and exciting, I love learning new things as much as I possibly can. I've always been like that since a young kid. But once I kind of learned something to a certain degree and there's no way to continue learning stuff in that, it becomes kind of boring. And I don't like that sort of time card punching aspect of work where you're coming and doing the same thing every day. So I managed to transition from being a process engineer to working at another factory, but in a completely different capacity. Instead of a process engineer at that factory, I went to work for a group that was part of the integration engineering department, which integration engineering is usually the people that are pulling data about like what the process engineers are doing and looking at the results at the end of the line, saying, how many units did we produce of widget A that we can sell? How many did we produce that we have to recycle? Or how many do we just have to discount in price because they're not quite up to par? This is in semiconductor manufacturing, so there's not a lot of discounting that happens. It does happen depending on what you're making, but for the most part, a failed chip on a wafer is scrap. It gets thrown away. If you have too many failed chips on a wafer, you scrap the entire wafer. If you have too many failed wafers in an entire run, you scrap the entire run, depending on what the problem is. So integration engineering, and particularly yield analysis, is focused on figuring out why. So it's all root cause analysis. Like, hey, this run that went through 1,600 steps in the factory over a period of 3 months. Well, there's 25 wafers in that run. Why did these 3 have a yield of 10% and the rest had a yield of 99%? That percentage is what's the ratio of good to bad chips on the entire wafer? So you're given the keys to the kingdom with data. You can pull data from any tool in the factory, going back years of data if you want. And you have to figure out what are the common paths through the factory. And each of those 1,600 stages, they could go through anywhere from one tool with 10 units on that tool to 50 tools with 8 units on each of those tools, depending on what the step is and what you're doing. So lots of paths that you can potentially go through the factory. And when I got started in doing that, was approaching that with the mindset of, well, I'm pretty good at like finding patterns in things, so I'll just, pull all the data and see if I can find commonality between, these, all the problem wafers went through this one tool. And that works to a certain degree with doing brute force analytics, where you're writing just basic SQL against massive databases and saying, what's the count of, the bad wafers that went through all the different chambers, and what pops up as the top 10. Well, I'll go and look in those tool logs and see if I see something weird. And that works while you're getting started. And the department that I joined, I was one of the first 3 people that joined it. They had just started it because it was a relatively new factory when I got there. And it's really easy to find stuff when your yields are kind of low and there's a lot of problems because it's a new factory. But once you start tearing down all that low-hanging fruit, it starts to become much less of a chance of you finding, oh, we have scrap wafers throughout the factory run. And it becomes like, that's all low-hanging fruit. You figure out like, oh, that tool had a messed up recipe for 3 days. Everything that went through it in that one chamber is bad. That's easy to find with just basic analytics. Fast forward a year and a half from there, none of that's happening anymore. Or if it is happening, we're catching it while it's running through the factory and scrapping the wafers in situ. So when we're looking at the end of the line yields, it's just patterns on wafers. And we're like, well, how do we get from an average of 96% yield to 98% yield? Ben and team, go figure out. And I was like, I have no idea. But I had learned all this stuff at a previous company about advanced statistical processes using SAS software. So got a bunch of licenses for that and started doing sort of old school machine learning.
Wait, you kicked off the SAS initiative at that company? Was it a team decision or?
It was just kind of a group discussion where we're saying, what tools do we need to figure this stuff out? It wasn't me being a hero, being like, this is the only way to do it. There's about 20 of us and all really smart people. We just sat down and we're like, what do we need to figure this stuff out? And we all tried a ton of different things. And I just had the benefit of having the training at a previous company from the institute that makes that software. So I had all their books and, even stuff that you can't get online. And I was just going through the training materials. There's stacks and stacks of books because we were all signed up for all those classes. So I was like, oh, geez, linear regression. Okay, in SAS, how do I do this with multivariate? All right, go to that chapter, look through the examples, and just started applying those techniques and refining them and getting more and more creative as time went on and exploring more of their software suite. And looking back on it now, I was like, man, I got a lot of exposure of a lot of different foundations of applied machine learning because there's so many different things that were going on at that factory with data. We had defect detection stuff where that's image processing. We're like, hey, we have the raw image of an SEM. Can we figure out if we align what we're expecting wafer to wafer on this particular coordinate shot, can we detect if there's differences in the, with a fixed aperture, can we determine if there's differences in resolution at this particular layer that we're getting a picture of? And we started to classify those. We didn't know what all this stuff was at the time. There's sort of precursor to, image classification as people know it today. And there were people at the time that were doing far more advanced stuff, but we were just sort of brute forcing our way through it by looking at reading docs, trying stuff out and seeing if we could save the factory money. And that was our end goal. And we did. Billions of dollars were saved in the 6 years that I worked there, with a great team of people that were, super smart.
That's crazy. Wait, question before we move on. A lot of these sort of anomaly detection systems, you often have to make a trade-off from a business perspective of a false positive rate versus a false negative rate versus essentially like success and failure. How did you guys think about detecting, how do you think about the trade-off between detecting something correctly versus detecting something incorrectly?
So I can't get into the full details of that. I'm still technically under NDA from that company, but
when does the NDA expire?
It's a 20-year NDA, actually.
Jesus.
So 12 years from now. Or no, maybe it's like 8 years from now. But there's processes in place when you're dealing with that amount of money in product, and when there's another big company that's paying you to make those devices. So there's no one person that decides to throw a wafer away. That wafer could be, if you're making some old tech, the wafer could be $10,000 because of the chips that are on it. If you're making something that's cutting edge, state of the art, that wafer could be $250,000, one wafer. And there's 400,000 wafers in the factory at any given time. So, you start saying like, oh, I think this is a problem. We got to scrap it. Executives are going to start saying, what are you doing? Like, every wafer you throw away, that's 2 years of your salary. A lot of scrutiny goes into decisions, as it should be. And major scrap events are decided by people extremely high up, like higher than the people that ran that factory. So what we were trying to do was not so much identify through eliminating false positives and false negatives of saying, well, we have a good idea of, we need to scrap this. It was more, where can we tie this back to, this defect that we detected, to let the owner of the tool that ran the processing right before this metrology and tell them, hey, you need to clean your tool.
Got it. That makes sense. So you would focus on not just identifying issues, but sort of alerting the creator of the tool to fix whatever the issue is.
Yeah, the maintainer of the tool.
Maintainer, got it.
So the process engineer, like the job that I used to do before that, and the technicians to say, hey, you need to clean this, or adjust something, or do something with your recipe so that you're not creating this problem.
It's interesting. The reason I asked about sort of false positive versus false negative rate is I'm working on a couple projects actually that all encompass this concept. And anytime that you have an automated system surfacing an action to the business, you want to make sure that there's confidence in that action. And if there's issues with the model, obviously that's a problem. But even if there aren't issues with the model, there's sort of a trade-off between inertia versus action that changes inertia. So it's really interesting to hear that you guys were doing this way back when, and it makes a lot of sense. In a physical system, you would want to make sure that any of your processes are optimal. So that's super cool.
Yeah, and stuff like defect detection on silicon wafers. The makers of the tools that do the metrology, back then it was computer vision, where it was trying to classify each individual defect, and it knew its exact location. But nowadays, those tool manufacturers have deep learning models embedded into the tools themselves that are shockingly accurate and can make predictions on, hey, I see this defect at this location. There's a 93% probability that this is going to kill the die if we continue processing it, and then make a determination of, if you send this to cleaning again before next processing stage, this will probably be fine. Or I'm detecting something here that is a device killer. I'm 100% confident that this die is dead, and it'll mark that even all the way through further metrology so that it doesn't keep on pinging on that. It'll say like, hey, this chip is dead, so we don't need to keep on looking at it. We know that there was a defect at layer 5.1 that caused, basically a bridge short between a source and a drain.
So you come in to the Navy, do stuff, leave, work in semiconductor processing, and you brought some statistical knowledge to that semiconductor processing organization. And after doing some quote unquote data science, I think you ran linear regression, so you're officially a data scientist. What happened next?
Then I got jobs back to back working as an actual data scientist, like job title, and both in completely different industries. And I learned a lot of different approaches to ML that had like nothing to do with what I was doing in factories. Stuff like dealing with text or dealing with graph algorithms. And the job that I got before working at Databricks was dealing with retail, where it's like, hey, we have a recommendation engine to build.
Ben is slowly dying over there. You all right?
It's a really bad cold.
Jeez.
Yeah. But that's where I got exposure to forecasting as well, where it's like, hey, inventory forecasting and sales forecasting. And the big difference between what I was doing before working at that company was I wasn't doing stuff that was just for internal use only. So at the factory, we're writing scripts that are building models, and we're triggering those via cron scheduler or just running these ad hoc, where you have a script and you're just like, hey, execute this. I want the results for everything that processed in the last 6 hours. But when I worked at the retail company, it's like, hey, we need to have predictions that are ready every day at 5 a.m. and you need to get this automated.
Got it. So that probably involves some software engineering.
So I had no idea how to do any of that. Like zero clue. I knew how to write basic functions in I knew how to do stuff in SAS at that time, and I knew how to do like basic Python stuff. And like I could write a simple function. I had never written a test for a function. I had never written a class. I had no idea how any of that stuff worked. And I had certainly never deployed anything. So I took it upon myself to do 3 separate things that sort of prepared me for doing that sort of work. One is I found some people that were really cool and would help me out with all the stupid questions I was going to ask. Second thing is I bought a bunch of books, and in the process of buying those books, I set up, based on the advice of mentors, to just build a bunch of projects. I'm like, hey, figure out how to do these things with the guidance of these books and asking them for help if I got really stuck. And then the third thing was look at a bunch of examples that were available on the internet. This wasn't reading through blog posts of the hello world for a library. This was somebody submitting an example of like an end-to-end deployment of an ML model. And also I just got to know a bunch of people in industry at tech meetups and stuff, and just start asking them questions. Like, oh, what's the tech stack that you use? Oh, how do you do this? And I'd listen to everything they said. right after talking to them, I'd take a bunch of notes, and then I knew over the next week or so, that was all the stuff that I didn't just have to go and read about, but I'd have to go and try it and break it. And by breaking, I mean every single thing that I tried the first time, I broke it. And you learn a lot. You learn how to read stack traces, you learn how to write tests. And in the process of learning those things about debugging, you start to almost subconsciously learn how to write better code.
Yeah, that I've definitely experienced that as well. After you break literally everything under the sun, you start sort of developing intuition on what will break when. That's interesting. So it sounds like your transition into the quote unquote data science world was completely organic. You didn't have this vision of becoming, well, data science probably wasn't even a thing then. Um, and you sort of brought statistical knowledge to physical processes. And then people were like, we actually want these statistical processes to run in a scheduled manner and ideally not break. And that's where software came in. Is that essentially the path you took?
I mean, the term data scientist, I've always found like really weird, because it's just this coined phrase that somebody came up with, and it just stuck, and people are like, "Oh, it's my job title now. I'm super cool." But many job titles over the last 50, 60, 70 years would classify today as data scientists, but they would be called different things. Like at the factory, we were called yield analysis engineers. It was data science that we were doing, and analytics. At other companies that I worked at some of those previous factories, there were statisticians on staff. They were building models. They were evaluating how things were behaving in the factory, using what we would call data science today. And researchers working for large institutions on large-scale compute clusters, they would definitely be called machine learning engineers today, or data scientists. And they were doing deep learning back in the 1970s on high compute clusters. And so a lot of people think, well, the job title just started in the last 15 years, data scientist, but people have been doing this stuff for a really long time. It's just cool now. It's even cooler now with everybody talking about chatbots.
Yeah, it's officially a buzzword, and that always helps because buzzwords originate from a process that existed for a while. It actually amazed me to learn. So I was sort of new to the Chat GPT world uh, when it 3 point whatever was released to the public, and it turns out that there was chatbots with similar or even more powerful functionality for years prior, and deep learning was invented in the 70s and was used. Actually, I don't know if it was invented in the 70s, but even crazier is some of the most cutting edge statistical methods, or at least methods that are still used today, were invented in the frickin' 20s. Like we really have been leveraging a lot of history of information and a lot of history of innovation and research.
It's easy for people to look at a new magical thing that comes out and wonder how it works, and wonder and sort of by default associate this new functionality as something that was just born from the team that built it. But if you were to ask any of the people on that team, they'll be the first to say, like, no, we used this awesome paper from these people, and they used these other 30 papers to come to this next decision. Everything grows on itself. And that's going to continue to happen. It's just how research works. That's how science works. And it's going to be interesting to see what the future holds. But the other line of questioning that you had was that sort of transition into this making stuff run in production, and what are the sorts of skills that had to be learned to get that to happen. And going through the process of learning how to write code that doesn't suck and understand new technologies relatively quickly so that it can be done in a way that isn't dangerous. It's relatively challenging to do that, and I would say I would not have been able to do it at all if I didn't have a couple of people that I could ask a lot of questions to. There's multiple different ways about that asking questions part that I don't think a lot of people outside of software development think about. So you can ask a question via, Slack or chat or email or in person face to face. Say, hey, I want to know more about X. Can you explain it to me? And I would argue that's the least efficient way of learning something when interacting with a mentor, because you're the one who's guiding what your bias is telling you know and you don't know. So our minds, particularly with technical things that we're supposed to, have a grasp on, we sort of compartmentalize things that we think that we have a really good handle on into this sort of bucket of, yeah, I know this. I've got this under control. And then we also know the things that we kind of have a fuzzy understanding of that we need more information on. But we have no idea generally about that vast ocean of things that we're ignorant about. The more that you know, and the further you go on your journey, you realize how deep that ocean is and how wide and long it is. And eventually you realize that there's oceans within oceans and you're never going to get to see them all. But for software engineers, one of the tools that's used not just for protecting your production code base and making sure that things that get deployed to production are going to work well, is a code review. We file a branch to merge to our main branch, and we have this pull request. Now, pull requests are, in my opinion, for people writing code, the single most efficient way of learning, because it exposes what you think you know, but you actually don't really know that well as the things that you have no idea, or that you didn't know there was a better way to do it, or that maybe the way that you were thinking about the design of this isn't necessarily wrong. It's just there's a way that makes the code more maintainable in the future.
Yeah, just to piggyback on that, it's really interesting that you say that's the most efficient way to learn. I am sort of junior in my career, but I've started managing a couple people, and it's been interesting to see what techniques they like versus what techniques I like versus what techniques lead to the best result short term versus the techniques that lead to the best result long term. So if I need something done in 2 hours, let's say, I say, do this, do this, do this, and then they go implement it. But they might not retain long-term understanding of why I was thinking this way, alternative designs, and that type of thing. So if you're investing in that person, it's often best to just say, try to figure it out, and then come back to me with ideas, and then you can steer. It's sort of the PR approach. So there's many different management styles, and basically how your mentor treats you says a lot about how they think about your future and your work. Because if they're investing in you, they're probably not telling you what to do.
Yeah, definitely. I mean, if you're a direct supervisor of somebody and you see them as a blood-filled version of ChatGPT 3.5, and you're like, hey, I need you to build, these 4 functions for me that do these things, and then write at least a dozen unit tests that cover, their functionality. That person's just going to be like, okay, I can do that. And they'll go off and do it. And they're just going to do one of two things. If they know how to do that already, they're going to pull from their reserves of knowledge, or maybe reference something that they've done in the past very similar to that. And they're just going to get it done really quick, and they're going to ship it out. And if it works, great. But if they don't know what they're doing with it, they don't have a good rapport with that supervisor to say, hey, I don't quite grok this. Can you walk me through how you would think about this? So they're going to default to what is the other avenue for them, which is Stack Overflow. They might win the Stack Overflow lottery, like the gold standard example Uh, if they have any sort of, you know, self-respect, they'll use that as a reference and rewrite what they're going to do based on that implementation, and write a bunch of comments in there to explain what's going on. And then also say, hey, I got this idea from this Stack Overflow post at this following link. But if they just don't care, they're going to just copy pasta. And that code is now perpetuated into yet another code base.
Wait, I have a quick question. So, and I'm curious if you experienced this as well. Throughout school, I was like relatively smart, but I think what my strength was, and also my weakness, was I was really good at quote unquote mastering things, but I was really bad at just getting a B plus or like an A minus. So I was really efficient to getting an A plus, but I was also I just needed to do a lot of studying and research to get to that level. And I couldn't sort of half-ass things. And so what I have been recently trying out is I've required customer work and just Databricks work that I have to do. And I just put on headphones, time box it, like literally set a timer on my computer and get it done. I don't care how it works. I don't care why it works. I don't care when it works. As long as it works, we're good to go. And then what I do is I try to reserve at least an hour a day, maybe more, to actually going at the pace that I enjoy. And so an example is going down a rabbit hole for, what was the most recent rabbit hole? For buffered loggers in Python, how those work. And I spent like 60 minutes of my full 60 minutes that day just creating a prototype, trying to break stuff, trying to explore stuff. Now I think I have a reasonable understanding of conceptually how they're designed, but there's 500 million other things that are relevant to buffered loggers that I just will not ever get to. So I've been dividing into going as fast as possible and not caring why things work, and then slowing down and actually enjoying the learning process, not under deadline. Do you do something similar, or do you learn everything relatively thoroughly before you actually implement in a production setting?
I wish. I don't know any. I personally don't know any software engineers that behave that way, that aren't still in school, that aren't like in a doctoral research program or something. When you're getting paid to write code, nobody cares how you do it except for the other people on your team. The people that are paying you are not the other people on your team. They are the management at the company. They expect that the code will work. They don't care how it works. They're not interested in that. They want a product. So because we work in a capitalist society, those products make us money, which gives us our salaries. And if you're not producing products to the pace at which your management expects, you won't be getting a salary anymore. So it's very important to put priority on product when you're developing software. And even in like developing models as well. You know, data scientists aren't immune to this either. They get a little bit more leeway, I think, because people generally in management don't understand what they're doing. People in management definitely understand the process of software development. It's been out long enough, and they know that, hey, they said it's going to take 3 weeks to do this. It's been 3.5 weeks. Where's the product? If you come back with, well, I wanted to understand more about this esoteric concept before I actually wrote the code, you might get away with that like 2 or 3 times at most companies. After that, they're going to be like, no hard feelings. There's the door. Rightfully so. Like, you can't do that. So it's all about learning the foundations and having a really good understanding of how to generally write code and solve problems with code. This isn't, hey, learn this language really well. Software engineers, nobody has a job title of Python software engineer or Java software engineer. I mean, I'm sure those job titles exist, but if you're a true professional software engineer, Doesn't matter what language it is. You just need to understand patterns of development, patterns of writing things, and how to figure something out in such a way that you can ship a product on time. Now, there's certain cool things that you get to do along the way where you're like, I really want to know how buffered readers work. If that comes up in a feature development cycle, you can spend a little time to learn what you need to learn about that, to be like, okay, using one of these to write a stream of data into, well, I need to understand, is there some sort of trigger that I need to dump, everything that's queued up into this out somewhere? How do I change the size of this? What's the impact to the system? And usually you just write some tests real quick or simulate some data and learn it that way of like, oh, this is the behavior of this. There are certain times where you would need to go deep on something like that. I mean, like really deep, if the solution to your problem was you need to implement your own buffering system. Like you can't use the one, or you have to extend the one that's built into the language. And there's all sorts of, that's where open source projects come from, is somebody being like, hey, the thing that's part of my language doesn't do what I need it to do, and I really need it to do these other things. And that's when you do that project where you're going so far down deep into the rabbit hole, you're interfacing with very base modules in a language that are, marked developer only, or, they're not generally interfaced with by most people that are using the language. And that stuff's cool. But if you were to do projects like that back to back over and over throughout like an entire year of working as a software engineer, I think you get burned out, because the mental load for doing that over and over with deadlines is pretty intense. Most good TLs are going to split up work like that among a team, so that at any given quarter, maybe 20% of your team is doing work like that. And then the next quarter, a different 20% of the team is doing work like that. You don't want to overload just a couple of people with the cool stuff, because the cool stuff can become not so cool if that's all you're doing. You just end up feeling exhausted by the end of the week, like mentally drained. Like, well, I was operating at this high level for this amount of time. Eventually, that no longer becomes cool. Can confirm. Right? Just like, I just want to turn on a stupid like documentary on Netflix and just vegetate state, just watching a screen with bright lights moving in front of me. I'm not paying attention to anything. So it's very important to not go down that deep when learning everything. And
it's super interesting you say you shouldn't do that. Since joining Databricks, I feel like my consumption of crap TV has really increased. And I kind of like it. Like it's, as long as I still have sort of a balanced and full life outside of work, it's really fun to just be constantly overwhelmed and going in every single day and sort of requiring to be at your peak capacity to output on time. And I mean, it's probably different for everyone, and maybe it's not sustainable. I've only been at Databricks for like, I don't know, 8 months or something. But yeah, I don't know. It's fun.
Well, the going deep into technical things is slightly different than the concept of just having an intense work pace. If you work at this company, you're going to have an intense work pace, regardless of what you're doing. There's a lot of stuff that goes on. But if you're spending 10 hours a day digging into the source code of something, because there's no documentation for this stuff. It's not like, oh, I can go to, the user guide of this library and they explain how they built it. No developer does that. Nobody has time for that. So if you're interfacing with low-level stuff or seeing how would I build something from scratch that meets this need, but the amount of complexity in that need is so severe that you're like, okay, I'm not just building this one thing. there's actually, 80 components that all need to be built and working together in concert at some point, but I can't build it all at the same time because nobody's going to review that PR that's 50,000 lines of code. So how do I break this problem up into 15 different component parts that I develop over a period of 3 months? There's only so many projects like that you can do and not feel mentally overwhelmed, where you're just focusing on this one thing for a really long period of time, and every day is just pure intensity. Uh, yeah, it's a lot.
One of the things that I've been really enjoying as well is with the pace of always having to learn new things, you start learning. It sounds kind of corny, but you start learning how to learn. You start finding patterns in what is valuable information and what is not. And maybe I'm just bad at that and always have been, question mark. But um, it's really cool to see how when you identify a component of knowledge, let's say, and let's take, I don't know, let's go with the buffered logging example. Knowing how it flushes to a CSV file, let's say, you don't really need to know that because it's just a call. It's a function call that's already written for you. But theoretically, if you didn't know that that is not relevant to your run process, you would have to go into the source code and see how it actually flushes to a reader or to a CSV file, let's say. So one of the really, really fun things that I've been enjoying is figuring out like that pattern recognition for when a piece of knowledge is relevant to your process versus is not. Did you cultivate that over time, or did you always have that, or do you not have that?
I think this is an interesting topic, but I've had this conversation with people in the past where they're like, "Hey, when you think about how something works, how does your brain work?" Or like, are you visual, or do you think about component pieces, or do you sort of hear somebody talking in your head from a different voice, or people have different internal mental modes of how they solve problems. And from a young age, I've always had this, I wouldn't call it a skill. It's just like how my brain works internally is when I think about something or I look at something and I want to start thinking about how it works, it's almost like my brain starts like creating a visual model of it in my head and starts disassembling it. And then I see how everything kind of fits together. Um, and but that same level of abstraction happens with stuff like software, which is why I could write code relatively efficiently and understand how things work, because that's what's going on inside my mental model is I'm looking at a function, but to me, when I look at that, it's like a box or cube that's moving over to one side, and then all of the places where it's called from, there's like strings being tied to other boxes that are using that. And then when I'm thinking about navigating through the code, um, I'm like a tightrope walker who's walking between each of the boxes and seeing, oh, what happens if I jump from this rope to this rope? Well, that's a different,
So what does a
logical,
box represent again?
like a function or a method in code,
Got it. So
or
a
it could be a
component.
class. Yeah,
Okay.
just something that is called. But that sort of visual and spatial uh, understanding of the world, that's just how my mind's always worked. And with that mental model, I kind of use it to think of other patterns that I can see. I'm like, oh, this is kind of like how this thing works. It's similar to this other thing that I understood about, you know, and kind of understand causality of using different things in different ways. Um, I don't know if that makes it easier for me to learn some of these concepts or harder. I don't have any other frame of reference. It's just how I think about things.
Yeah, that's super interesting. I wonder, it'd be cool to get a tour of some smart people's brains and see what structures they leverage because a lot of it just sort of seems like magic. They just produce a good output. What like they think critically, they think quickly, and yeah, it's just so crazy that different people can have a visual model versus sort of an completely intuition based model. Like I don't have boxes. I have nodes and edges, and I sort of think about how concepts connect via this like soft. Wow, I actually haven't thought about this before. So, innovation on the podcast, but it's sort of like a weird, almost kernel based connection between different areas of a graph, where the kernel transforms the shape so that it's congruent and fits like a puzzle. But it's definitely not as structured as boxes, as you say. It's very high dimensional, weird space.
Yeah, when I was a kid, I used to look at stuff like appliances that were around the house or things that were in my dad's garage, like tools, like the lawnmower. And mentally, I remember, and it still happens to today when I'm looking at something that I know is like something's broken. I got to go out and fix it, or figure out what's going on with this thing. I still like my mind just still does it. It like disassembles it in 3-dimensional space inside my mind, and I can kind of visualize what I think are different components that are within that. I remember the first time realizing that there was something weird with that was actually looking at the lawnmower in the garage and just seeing it from the top. And I'm like, how does it cut grass? And then, my mind just started like taking the cover off. And then inside there was this thing with a I didn't know what it was called, but it's like, oh, this is an engine and it has a rotor attached to it. And there's pistons attached to the rotor and it's a camshaft. And, there's a blade spinning around, but it sort of hazily deconstructed this. And then lifting up the lawnmower onto its side, validating that like, yeah, that's how it works. It like spins like this, and there's this shaft that goes into this thing. I open the cover up. So my mind still does that. Sometimes it's kind of distracting and annoying, but it helps me kind of visualize, which was a boon when talking to a lot of customers at Databricks when they speak in abstract terms of something complex that they want to build. I'm not building those horrible PowerPoint presentations of architectural diagrams that drive me up a wall because they're never detailed enough. But I'm building like what I think the components are actually doing when they're sending, a packet of JSON data from one place to another. What do these things do? Like, okay, you have all this data, you're operating structured streaming on a Spark cluster, and then you're connected to Kinesis that's sharded out to 500 nodes. Which worker gets which packet of data and how does it do retry policy? And I'm just visualizing that like, oh, here's all these VMs. It's 500 boxes. And they all are shooting out all of these strings to all of these different worker nodes that is a fixed size that can auto scale as well. So I'm mentally imagining boxes just popping in and popping out of existence on those connections. And then just seeing little bits of packets of data moving to them and then going back the other way to do a retry, fetch from a particular shard with an offset. So I don't know. Maybe I'm crazy. That's just how my brain works.
This is wild. I remember one of the first times I ever heard Ben talk about something that I know something about. I was like, holy shit, this guy really knows his stuff. And then he did it for like 500 more topics. And every single time he used so much complex technology. I was like, this man just has a Rolodex in his brain. But it turns out that he just decomposes everything into a 3D Iron Man type model. That's insane. I didn't know that. That's super cool.
I'm just like a visuospatial like sort of person, which means I'm absolute garbage at stuff like learning foreign languages. I'm terrible at that. I suck at art, like badly suck at art. My brain is just not wired for stuff like that. I can be creative when thinking about things that are spatial in nature. So constructing code is spatial, for me, at least it is. And coming up with ideas about how to solve problems like that works. But doing stuff that is unstructured, like art, not good. But music makes sense to me because music is structural. So when I listen to something like a symphony, I'm this is like the episode of Mind Talk. I've told this to a couple of people and it's blown their minds. But when I hear a 40-piece orchestra, I'm actually hearing or seeing in my mind a 40-person orchestra and, the 18 different components.
Hell?
But I'm listening to each person individually. So when I'm listening to the music, I'm like seeing that person playing. Like this person's playing, the second violin, and they're also playing along with 4 other people, and I can hear that line in the music, which makes music really fun when you listen to complex stuff like classical music, and it makes music really boring when you listen to crappy pop music. But yeah, another weird anecdote.
Wait, so do you find complexity attractive?
In witnessing, yes. In creating, no.
Why in creating? Because theoretically, witnessing, like, why are they different?
My favorite thing is a simple solution to a complex topic. Or sort of there's beauty in simplicity.
Because all the pieces are working in harmony to a simple outcome?
Yeah. Got it. So if we're going to continue with the music theme, what if I had you as the conductor and the writer of music for an orchestra playing, and I told you, hey, I want you to create the most complex and discordant sound that you possibly can. The most effective way to do that is to have each instrument group of the orchestra starting at the lowest C that's available to be played. Probably the double basses out there playing their lowest note. Maybe that's an E, I don't remember. But each subsequent instrument playing 1/2 step away from each other, and just say, hey, play random notes. Is that complex? Yeah. There's a lot of things going on. One would say it's pure chaos. That would probably drive me to run out of that room. Like, I would not be able to deal with that. It would sound so bad to me, and there would have no order or beauty to it. There's entire genres of music that I just can't listen to because it's either, ridiculously simplistic and formulaic, and it's just repetitive and annoying, or it's intentionally written in such a way to be in violation of the terms of quality art. It's like somebody sort of trolling an audience by like, what if I play this thing that is creating not just tension and dissonance, but just pure chaos for a bit, and then I don't resolve that. It's like, why are you doing this? You're just doing this because you can. But that's complexity for the sake of complexity. People do that in code as well. They write stuff that they may know there's a simpler way to do it, but they want to show off. They want people to look at their code and be like, wow, this person is super advanced and they're super clever. But anybody who's actually super advanced and super clever with software, who sees something like that and knows they're going to know the better way to do it or the simpler way to do it, they look at that and they're like, maybe it's a super junior person who wrote that. And they don't know any better. But if they know who that person was that wrote it, and they know that they should know better than to do that, you're just like, what an idiot. Like, what a complete asshole. Like, why would you write code like that?
Yeah, so it's taking this to the maximum meta of that statement. So let's say you start off with sort of a fixed type of brain in childhood. And then throughout life, you can certainly augment skills, but typically the way your brain works is the way your brain works. And I am of the side that you can actually do a lot to change how the fundamental nature of your brain operates, but it takes time and you need to be exposed to a specific environment for a long period of time. One thing that I think that people never freaking work on, and it's really, really high ROI and kind of annoying that this isn't more pop culture-y, but changing the goals that you shoot for. So like Ben just mentioned, If you are looking to solve a problem efficiently, you will never write unnecessarily complex code. But if you examine the rationale for you writing that complex code, it's, well, I'm probably a little insecure about my code writing abilities. I want to try this new thing that I might not know works or doesn't work, and anything else that's wrapped up into creating a suboptimal solution. Those are the issues. It's not your skill set. It's your desire for output and what output is good to you. And so one of the things that I've been just playing around with over the past couple of years is reframing what I strive towards in the hope of having an optimal result. And that's a very like hand wavy description of it, but it's really, really valuable. If you shoot for the right things, often the results come.
And to add to that, I would just say that the vast majority of professional software engineers are not under the illusion that what they're writing is the optimal solution. Anything that you create is usually under a certain state of duress, right? You're like, you need to get this thing shipped. You need to make sure your tests pass. You need to make sure that like you're doing everything you can within that deadline to get this thing out there. And if the pursuit is the most perfect code at all times, you're probably going to miss your deadline. And if you're the person writing the code, you're going to miss stuff. We all have, creator bias. And it's not because we think we're so good. It's because your mind went down a path while writing this thing that you're not constantly looking back at where you went down that entire path to be like, hey, did I clean up all of those branches back there? Like, I remember I went off to the right there for a minute, and then I had to go back to this Y in the road and then move down this other path. Did I trash that right path that I went down? So that's what peer review's for. A fresh set of eyes that's coming in and looking at it and be like, hey, dude, I don't think this code is actually used anymore, or I don't think you need to catch this exception because this shouldn't throw anymore. That whole process of shipping for other people to review code that's not optimal, or that is not like the best that you could do if given infinite time and perfect solitude and wonderful health while you're writing it. You have to basically, the most important tip that I have for people is don't be afraid of what people are going to think about what you're producing. Realize that everybody is seeing it the same way, provided that you're a nice person and people want to work with you. If you're nice and you're cool, everybody just wants you to continue being nice and cool to them. So they're going to be nice and cool to you back. And they just want us to make sure that what you're producing is good, so that, the product works correctly. But they also want to make it so that you understand what you missed, or teach you a better way of doing something by saying, hey, did you think of this? Or could we try this? So long as you can get out of your own way with feedback. And even if you are producing something that you don't fully understand, and realize that, if somebody else sees that, they're not going to be like, man, Michael just checked this code in. What a muppet. Did you see how jacked up this was? Nobody is thinking that. I promise you. Nobody who matters thinks that. If you're sending it to people who are doing peer reviews that are your peers, they're going to be like, hey, dude, did you think of, there's this, yeah, and I see you wrote all this stuff, this whole function. There's this thing in the native library that does this exact thing. And they're not going to say it does it better than how you implemented it. They're going to say it does this so that you don't have to, which is a hint of you don't want to maintain what you just built because now you own it. And it's another thing that could break when a new version of the library gets released. You now have to update that, because it's going to break. It's going to, deprecate. So you're going to get all this great feedback from people that you're cool with and that are cool with you. That's why I said earlier on, that's the fastest way to learn is getting out of your own way.
Yeah. I guess I agree. And even if people do shit on your code, that's fine. Like
Yeah, don't take it
they might say it
personally.
in a rude way, but yeah, don't take it personally and take the nugget of information that they do have and learn from it.
Yeah, the only time to completely disregard comments on things that you produce is if somebody is just saying something that's just trying to attack you. It's an ad hominem attack of like, why did you build this? This is dumb. I built something better. It's like, okay, I'll take a look at what you built, but that's not what I was told to do. I was told by my boss to build this thing. Are they aware of what you built? And usually the answer is yes. And the boss is like, I don't like that guy, you know. So if somebody's being a jerk just to be a jerk, you can usually tell because there's nothing constructive that they're producing. They just say, this sucks. Um, so it's good to push back on people like that and say, could you elucidate? Could you tell me a little bit more about why this doesn't meet the needs or why you don't like this? And people that are doing it just to hate on something, they typically can't answer that question because they either don't know, what could potentially be wrong and they're just being a jerk, or they want to disengage from that conversation as soon as possible. Either way, you win.
All right, so we're coming up on time, so I will try to wrap. This was a fun conversation. Yeah, so some of the nuggets that I thought were interesting were the way that Ben learned early in his career was first find people to help you. They can guide you on projects and also provide feedback. Second is buy a bunch of books. I'm a fan of blog posts, but books are really, really good when you have to go deep. And then third, go on the internet and try to implement stuff that's already out there. It's rare that there are code repositories that have super in-depth or cutting-edge topics. But at the same time, open source technology is pretty advanced. So you can find some cool stuff out there. The other component that we talked about was sort of ways to ask questions and whether that's from the mentor or mentee perspective. And so we're going to take the mentor perspective in this summary. If you are looking to invest in the people you are or that report to you, explaining how to do stuff directly is probably not the best option. Throwing them in the deep end is a common approach because it's very easy for mentors to do that and then just go about their day. But theoretically, a middle ground of creating sort of sandbox environments where your direct report can play and learn in a structured manner, that's typically the best way to manage someone for growth. But everybody has different styles and each person is different. So tailoring your style to that person is super relevant. So I think that concludes it. Ben, do you have any final thoughts?
No, it's a good summary.
Cool. All right. Well, until next time, it's been Michael Burke and my co-host,
Ben Wilson.
and have a good day, everyone.
Take it easy.